start from so it's the second action. We need that. We'll probably won't modify what we have. All right, let's get started. How's it going, everybody? Good? Good. Homework due tomorrow? Hopefully that's good. Yeah. You're like, oh, was that good? No. Yeah. Like, the one thing good about it is that it's the last time. And then summaries next week, and then projects. TAs are doing a great job. Rely on them if you need anything. But I'm always happy to answer questions if you got in the class at the end. Okay, so we're going to get started in our second part of neural machine translation. So, last time we talked about like what's known as seek-to-seek. So it's like an encoding-decoding method for sequences. Can be used for doing any kind of sequence-to-sequence transformation. Here, the example, of course, is for translation of one language into another, but you know, these kind of techniques definitely generalize. But today we'll continue to focus on just translation of languages. And if you recall this, we ended with this last time. Even with those great kinds of models, things can still go bad. And there were like three main reasons why things might go bad. I mean, there's actually lots of reasons why things might go bad, but here's like three things that have been tackled since the seek-to-seek models, which came out in 2014. So one is how to deal with vocabulary size. So like we talked about last time, one of the challenges here is that vocabularies can be quite large. You know, they can be hundreds of thousands of words or terms in a vocabulary, and that can be really difficult to deal with, like with the softmax layer, or with softmax classifier, because you know, there's a lot of weights for one, that adds a lot of weights. The other thing is, you know, the probability just gets diffused over hundreds of thousands of options, and can make it difficult to learn. So vocabulary size is a trick. Just long sentences are hard to translate. Just the longer term temporal dependencies they're just difficult in general for anything, especially for language where long-term temporal correlations actually have meaning for the sentence. So getting those right is important, and that's hard. So you know, how can we make progress on that? And then also just language complexity. There's just language is just complex itself, and you know, just dealing with some of the issues like when you go between different languages, you know, you change alphabets and you change grammars and things like that. So, you know, are there some things that we can do to handle more of the complexity of language? So we're going to talk about a technique for each of these. What we'll talk about for the vocabulary size problem is a really pretty straightforward technique for dealing with rare words. And here called the copy mechanism, and we'll go through the details of that. For sentence length, a technique for dealing with this that works really well is adding an attention mechanism to the decoding. So basically, it's going to allow the decoder to focus in on certain word representations in the encoder network. And then for the language complexity, there's going to be some character level models as well as word translation models. So these will all work together to give us state-of-the-art results. So, yeah, that's what we were talking about, right? So when we did convolutional networks, lots of the examples that we talked about and we were interested in, like lots of the attention is on how well models do on the image classification challenge, the ImageNet challenge, and there you get 1,000 categories. Seems like a lot, but it's like nothing compared to language. There's just so many words, especially across multiple languages, multiple vocabularies. So it's just a very different thing. So yeah, what to do about this? So this is what is typically done. So by the way, this is like a standard example in this, and from English to French, or French to English. And honestly, when I looked at this for the first time, I was like, what on earth is ecotax portico? But it turns out, a little bit of research I did on this, that in France a couple of years ago, it was like, there was a tax called the ecotax, for roads, and they set up road, it's like these, it's like video cameras basically over the highway to see who was driving on the roads, and then if you're driving on them, you get taxed. Anyways, that was called a portico in French, and it was over the Pont de Bouilly or whatever, however you say that. So, anyways, for whatever reason, this becomes like a standard example in talking about this. But there's your little bit of history. But the point here that this is illustrating is that there's like a lot of rare words here, right? We don't talk about ecotax very often. We don't talk about porticos or portiques or whatever, although apparently this wasn't rare in English, which seems weird. But and then like this location is rare. So what typically happens, so like state of the art, like around 2014 when we're talking about seek-to-seek models, is to go through your corpus and just calculate a histogram on all your words in the vocabulary, and then there's just like a cutoff. You say like after so a histogram basically gives you like the frequency of that word within the corpus, and then at a certain frequency you say that word is rare and we're not going to learn to translate it. We're just going to replace it with a token, usually something that's indicating that it's unknown. Unk. The first 3 letters of unknown. And this would be like your translation. Like you'd have all these unknowns in it if it was rare. So, like not ideal, right? We want to be able to deal with this. Oh, and of course the reason why we do this is because we can replace all of these rare words that that don't show up very often. So our blue score won't be affected by this very much. We replace all of those with just this one symbol. So our softmax layer goes from having tens of millions of entries to whatever the size of vocabulary we want, and then just this extra class. So it's just a convenience thing, but we can do better. And it turns out the mechanism is like not all that tricky. So it's this thing called a copy mechanism for the rare words. And basically, again, mostly words that we have no idea what they mean. And instead of just replacing them with unknowns, what we do is we replace them with tokens that represent that keep track of the position that they were in the original sentence. And then when we do the translation, there is at least some understanding about like the alignment of the grammars, right? So like in English, we might have our adjective come first, but in French, we would have it come second. And so these kinds of alignments are important to keep track of. So we know that like the unknown in the English, the ecotax should show up after, should show up here compared to this unknown here. So and then this unknown right here, this is just, that's kept track of separately. So you do this thing where you're just keeping track of where all your unknowns are, where they should go in their translated sentence. So it's still an unknown where they should go. So you still, basically, this is like basically the same. But then, after that's done, what you do is, so for instance, this rare word ecotax, you basically do like a dictionary translation. You basically just like look up what ecotax should translate to in French, and you put it in the right spot in the translated sentence. So that's for like words that are like typical. Let's see, like what's the right way to say it? Just like like parts of speech like adjectives or nouns or verbs. And then you have things like proper names. That's just an identity copy, right? Like this is just some proper name, so it probably doesn't translate to some other word in the other language. It's probably like the same word. We don't usually translate like a French name to an English name or vice versa. So those kinds of things just get copied explicitly from one to the other. And if you do this, you actually get state-of-the-art neural machine translation results. So if you remember, when we looked at this last time, we had like our best statistical machine translation system got a blue score on this English to French translation task of 37. And just by doing this, where we now include this like dictionary lookup for, so it's alignment, keep track of alignment, dictionary lookup for most words, and then like for proper nouns doing just a copy of like an identity transformation. We actually add half a blue score to that. So you get, for the first time, a neural machine translation system that's actually state-of-the-art. So it's beating the statistical machine translation systems. Maybe it seems kind of funny because it doesn't so much feel like end-to-end learning anymore, right? Because it's like you do end-to-end learning and then you have this additional step. But it's way less of a Rube Goldberg machine than like the statistical machine translation systems. And yeah, it's a pretty exciting advancement. And here's the kind of things that you see happening. So like here is, so what we're going to see here is we're going to see the source in English. We're going to see a human translation into French. This would be the thing that you would use to compare and calculate your blue score from. We'll see a translation from like the typical seek-to-seek, and then a translation where you do this copy mechanism mapping. So in this case, we're looking at the rare word cataract, right? So the human translates it correctly, obviously. And this gets mapped to this unknown symbol here. And yeah, so again, like we didn't learn, like, so we learned to in the translation, we learned to produce the unknown symbol for that, but we didn't know, we didn't learn to produce the word the French word cataract. Somebody speaks French can tell me how to pronounce that. But we know at least we're keeping track of that and where it is. And then when we do this copy mechanism, we go, oh, I know, I can just look this up in a dictionary, English to French translation, and put the right word there, and all of a sudden my blue score goes up by a little bit, and you do this a bunch of times and you get state-of-the-art performance. This also works for things like, here's a article that has the bank JP Morgan in it, and again, this is just showing how, it's a name of a business, so this usually doesn't get translated from one language to another, it's always the same. So it recognizes that it's a proper name that way, its location is kept track of, and then you just do this copy. So that's the other mechanism too. So awesome. State-of-the-art stuff. But there's also, obviously, there can be some problems. So here, what happens is you get a problem with the wrong alignment. So if you look up at the source there's just some, whatever. There's just some, sentence, But what happens is that there's this word was and abandoning. And that gets translated here into French as just one word for that like past, I don't know what the right grammar, what the right word is for that part of speech. But to that, to that word in the past, it gets done just once. And what happens is like there's this problem in translation because it produces two unknown symbols for just that, for what is really just one here. And what happens is when we do this copy mechanism, it instead of keeping track of abandoning, it keeps track of was, and it puts the French translation of was there rather than the French translation of was abandoning. So like there's some issues here, and you could go through, you can imagine like a researcher going through like each of the cases where it failed and try to add like some heuristic for dealing with it and maybe make it a little bit better. But these are some of the things that go wrong with this. But again, just by adding this little tweak, you get state-of-the-art neural machine translation. Okay, questions about that? Yeah.
So in traditional machine translation, do they have the problem of just having unknowns everywhere?
Like a statistical machine translation?
Yeah.
No, because there you don't deal with the sentence globally. Like here, you deal with the sentence as a whole, right? And there, in that setting, what you typically do is like you break this up into all the parts of speech. You deal with them all separately. Then you sort of have, I don't know, you have like lots of statistical models for building back up the sentence in the other language that are that represent like the rules of the other language, right? So like no, this doesn't exist there. Yeah, I mean you have things like dictionary lookup for everything, right? So you have no unknowns. Other questions? Okay, so that's basically a solution, a pretty good solution to the first problem. Okay, so the next one, sentence length. So this is the problem of sentences being very long and the temporal correlations being hard to learn. So how to deal with this? Well, a way of dealing with this is to add an intention mechanism. Yeah, that's right. So the translation quality tends to degrade with the length of the sentence. So what we're going to do is just sort of show you a technique where what we'll do is we'll not only take the hidden state. So as we move along in the decoder to pit and build up the state there that will feed into the softmax layer for producing the next word, we're not only going to take just the hidden state that's coming from the previous word, but we're going to look back into the encoder and we're going to use bits and pieces of what was in the encoder for this translation, and combine it with our current hidden state to produce like a new hidden state that will feed in and hopefully give us better translations. So this was done by my good buddy Joshua up there. Actually, he probably hardly knows me, but no, I've had various meetings with him. Hopefully, he wouldn't actually say things like, "Oh yeah, like I once upon a time talked to him." What I'm showing you in this graph is a result coming out of this paper here, and I'm going to go through here and tell you about the attention mechanism, what it is. But this is just like the result, right? So you have sentence length here, and what you have is the bluest score. So this would be like average blue score over sentences of length. This is like 30, 40, and so on. So you can see like with seek-to-seek type models, you're getting the blue score, it goes down by quite a bit as the sentences get longer and longer. But what you see with this attention mechanism is that it sort of plateaus and stays up high even as the sentences get longer. So this is definitely solving this problem. And then that matrix over there is like something like a heat map for the attention coefficients produced in this So like here's a way of, or here's basically what happens. So this is set up so that, okay, so here's the source phrase, I am a student, and we've already translated, or we've already produced one word in this target phrase, je, and now we're going to concentrate on like what we would do with including this intention mechanism to produce this new hidden state that will be used to predict the next term of the sequence. So the way this works is that you take the current hidden state coming out of, you do this per layer, but we're just focusing on this layer here. Take this current hidden state right here, and then you have some function for producing something like the similarity between that and this. It's some score. And just a way of comparing these vectors. And you do that, so remember this is going back to looking at the hidden state associated with the first term of the source translation, and then we're going to do this for all of them. The second, the third, the fourth, and however many there were, we would do this. And these are going to produce non-negative values. And then what we're going to do is turn those into like probabilities. So we're just going to divide by the sum of them all. And it works out nicely in this case. And then what we're going to do is we're going to use those weights as a way of basically building up a new, what's called a context vector, but think of it as like a new hidden state. So it's going to take those weights. So think of these as all as like vectors here, including the current hidden state. And we're going to multiply these hidden vectors by this learned score, and then we're going to combine it with the current hidden state, and that is what is going to be fed to the next state for the term that we want to produce. So instead of it just being what's coming out of here, there's an additional mechanism. So remember that the thing that's coming out here is already knows about these things here. Like it's already got, like this state has been built up by like think of it as transformations from this like initial state onward. So this already has some information here. This is an additional way of taking those same states and then just learning learning linear combinations of them to add into here that might boost our ability to translate when we add that into the hidden state. And then, just like normal, there's a softmax that uses that state to then make a prediction to assign probabilities to the entire vocabulary, and then we pick the one with the highest probability. And it seems to work actually pretty well. So there's different ways of doing this. What I just showed you was like use all the sources. You can choose to use subsets of it. This paper here goes through and compares a bunch of them. And the important thing here to see is that, again, this is like the results that are being anticipated here, but this time in using blue scores that are compared to the best ones. This is actually not the best one. This must be for neural translation. Anyways, so these were like the early scores for this task, and without attention, but you can see how this gets totally boosted by attention. All of them. So these are like these are. Let's see what's right. It says. This is one without attention, and then there's a couple different ones with different types of attention. Like this is like those different ways of thinking about the combinations of or which subsets you would focus on. And here's some best. Anyways, adding this mechanism will allow you to learn like which parts of the encoder to focus on improves your blue score, and you get nice things like the following. So this is for a different task, unfortunately, and I'm not sure why I switched from the English-French translation to the English-German one, but whatever. It is what it is. So this makes a point about names being translated correctly, which is kind of funny because we just spent a lot of time talking about how you use the copy mechanism to do proper names, but maybe in this setting there was some name translation. But the important thing is this is really cool. So you get in these kinds of systems you tend to get things like the following, where you get a lot more of the doubly negated phrases translated correctly. So the source here has a not incompatible, right? So there's double negative, right? Not, and then it's not compatible, it's not incompatible. So it's actually compatible, right? So this is just showing how these attention mechanisms, when added, actually get these kinds of things correct. So in these systems with attention, there's an appropriate translation there, which I don't speak German, so I don't know that it is, but you can see that this one has an un and this one doesn't. So hopefully, if anybody speaks German, they can look at that and say, yeah, that's the right way to have done it. But what we've noticed is that these things kind of get picked up. And what's also interesting is that it did it more succinctly than, say, the human translator did. So apparently, if you spoke German, you'd see that this whole thing right here was about, I guess not this whole thing, but maybe this part right here was this nicht ihm, blah, 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 was a very long way to say that part about not being incompatible, but these translation systems seem to do a better job of it. So, anyways, that's attention. And this is like the attention that we've seen, when we were looking at when we were doing the captioning of images. Remember, we represented our images with a matrix of locations within the image and features for those locations, and there was this whole cycle of learning that took those representations of the image, of the locations in the image, and then learned weights that combined them together, and use that to help caption the image. And you could use it. It was cool because you could use it to show what parts of the image it seemed to focus on when it was producing certain words. This is very, very similar to that technique. So yeah, and attention. I don't know that attention itself has a very succinct way of saying. It's a succinct way of defining when you have attention in your model, when you don't. But it just tends to be these kinds of methods that within the end-to-end learning, learn to focus in on certain parts of representations of whatever the problem is that you're doing. So anyways, that is that. Any questions about that? Yeah.
So this sounds like kind of what LSTMs were trying to do in terms of get that dependence. Why is it not possible for a vanilla LSTM to just learn that dependence instead of doing the first?
Yeah. So remember, go back. Remember, in an LSTM, it's a good question. So in an LSTM, you're if we were using LSTMs here to do this, which they are being used, the LSTM, the cell, each one of these is a cell, is an LSTM cell, right? So within each of these, there's there's this calculation going on. So there's basically two states being passed forward here. One is the hidden state, and one is the cell state. And the LSTM is about gates on how to combine the cell state and the hidden state together to produce the new cell state and the new hidden state. But it's still a local calculation for the cell, right? So it does better for long-term dependencies because one, you have these two different states that you're tracking, but two, because it's saying it's like there's a local attention mechanism saying which parts of the self state to pay attention to and which ones not to. This is different. This is saying not only do we have that mechanism to produce the local state, but we have a mechanism for combining all the previous states with that local state to produce the new state. So it's like, yeah, it's like a meta LSTM in some. I mean, that's a really loose way to say it, but it's like there's another layer on top that's allowing you to look further back, and at every step when you're producing a hidden state, you just allow yourself access to all of the previous states to make that translation. So that's how it's different. Yeah, and definitely what's happening here, if it's not clear, these aren't just like plain vanilla RNNs here. This isn't just like a single sigmoid in here. These are typically done with LSTM or GRU cells in all of these. Okay, oops. Okay, and then, yeah, we're going to finish way early. Hopefully that's good. Okay, and then the final problem here, the language complexity problem. So, so this is the problem where we just need like our networks just need to do more to deal with certain problems in language, like the fact that there's just like a very So in particular, like what's going to be dealt with here is what's known as like the open vocabulary problem. So vocabularies are very large. We've talked about that, but in some sense they're like open, right? So even though there's like all these rules for really how to do things, we do all kinds of other things when using like we don't like especially like written text. We don't always follow grammar rules properly. We don't spell things correctly. We might do like here's like some example of this, right? This is still good. We all recognize it immediately, but it's like someone might write it a little differently. And our systems, if they're trying to learn statistical correlations or statistical relationships between things, and these kinds of things can be very difficult to deal with because you might only see it like a couple of times or one time. So how to do that? And I'm actually not sure what language this is. Anybody recognize it? Nobody? But it feels a little bit like German, right? Like in German, you can make words out of. We do this in English too, I guess. But I guess in German, I've seen this a bunch where you just take a bunch of German words and you put them all together. Now you have a new German word, and that's a pretty typical thing to do. This is definitely not German, but yeah. You could do this thing where you can concatenate words, and you should be able to like deal with that because there are a whole bunch of other words in here that we should be able to recognize. So how to deal with this? Well, a way to deal with it, there were previous ways, but a way to deal with it is the following. So to just do word translation like we typically do, and then for the rare words, and this would be not just the rare words, but like the words that we have low confidence in through like our alignment, like our alignment and dictionary translation piece. We're actually going to rely on doing a character-to-character translation. So this is still seek to seek, but instead of it being we're representing words, so it's going to be like alphabet to alphabet. So instead of it being vocabulary to vocabulary, it's going to be alphabet to alphabet. And it actually gives massive, massive improvement it's funny because now this changes one more time to a different task. This is English-Czech. So, let's see, there was something there. Yeah, I didn't show it here. Maybe this is Czech. Probably is actually Czech when I think about it. And like it's showing things like sometimes proper names do have a proper translation in the other system. Anyways, so I don't know why they keep. It's like the same group of people. Like you've seen this guy's face many times. It's the same group of people, but they keep changing from like one task to the other. Maybe English to French got too easy, so now you go to something harder like English to German, and then maybe even harder English to Czech. But the point is that you have this hybrid system. So you have your word level seek-to-seek model with all the extras. And then when you get to something that's rare and can't just be easily looked up, then you resort to another model that's trained as like a component of within this. So you have another seek-to-seek that's just, again, going from alphabet to alphabet. And it uses the same types of cues, like, there's a start symbol, there's an end symbol, and, this is also like seek-to-seek, so this is all like LSTM or GRU cells, and they're stacked, and they just form, like they're just a smaller component here when needed. So it's like this piece of the network can be swapped out at any time, when needed. And it can all be trained end to end. So, yeah, this is just saying that like basically they're initialized in the same way, and they use embeddings in the same way. This on the fly just is referring to the fact that like you just at any point that it's needed when doing the translations, you just swap out this cell with this other network. Does that make sense? So it's like so like the graph, this computation graph basically changes for every phrase. So like there's this graph right here associated with the word level. There's this graph associated with the character level, and then you basically like embed this character computation graph into the word computation graph when needed. So sometimes, for some examples, gradients will be back propagated through, through this part, and sometimes it won't. So it's a bit complicated for training, for sure, but can be done. And yeah, this is just saying that, we continue to use this unknown word here just as like a way of recognizing like these are the things that need to be word translated, character translated. So what's cool about this is the following. So here's our English-Czech. So a similar set of translated sentences from English into Czech, and here is like the best word level neural machine translation system on this. Getting a blue score of 18.8. So this was like state of the art, and I'm not exactly sure what this is. Definitely seek-to-seek, but I'm not exactly sure that like what this means is 3x data through systems. But this is more like what we know here is these seek-to-seek where you have a single model doing this with a large vocabulary unknown replace. So the blue score here is a 15.7, not as good as this like state of the art at the time. If you ensemble these models together so that you have like you use like your most likely translation, you get a bit better. Not quite state of the art, but a little bit better. And then if you just do character-based, that was word-based. If you just do character-based neural machine translation, so seek-to-seek, this is the blue score you get. So it actually is a tiny bit better than just a single model word level. So that's kind of interesting. Notice this right here, 600 step back prop. So what that means is that it's truncated after 600 steps. So like, you don't propagate the gradient all the way back. That just would take too long. 600 steps, I can't believe it's taking that long. That's a lot. But yeah, so truncated after 600 steps, you don't propagate it further. But if you now do a hybrid of the two, like we just described, then the blue score you get is on this task is a 19.6, which is almost a blue point higher than that initial system. Actually, I guess this one right here is the SMT, the statistical machine translation system, and then these are the machine translations. So that's awesome. And that's just for a single model. And if you ensemble them, you get basically another point out of that. And again, take the most likely translation is determined by a loss. So yeah, so that's state of the art. That's state of the art, like as of like the end of 2016, beginning of 2017. It's been a year and a half since then, and there's been other there have been other like techniques and tweaks, but these are some of like the major tools that are used to do state of the art neural machine translation. And I don't think there's been like some, at least not that I'm aware of. There could easily be, but I'm just not aware of it. Like something that's really been able to make big progress in this area. Okay, so yeah, that's it. So basic seek-to-seek, you augment it with these different these different types of techniques, and you definitely get state-of-the-art neural machine translation. So this is better than statistical machine translation. It should be noted though that it's not better than human, and the reason for that is like in terms of the blue score, like you really can't do better than human on the blue score, right? Like what you can do is you can get like 100%, right? Like that's like, so the blue score, like the best you can do is to get 100. That would mean that you got exactly every single word exactly as the human did it. But the point here is that like in translation, it's like a many-to-many mapping, right? So it's like there are many ways of writing it in the source language, and there's many ways of translating it into the target language, right? So it's like the measure here is not exactly what we would want to say, like to get exact precision. All we can say is like for this task set up with so like the translations are already established. This is how well we do compared to it, and that's unlike some of these other systems where again humans were the ones annotating, but there was some level, like it's a lot easier to say like whether a person, it's a lot easier to say there's a dog or there's not a dog in that image. It's a lot harder problem to say like you correctly translated this. So there's not this like measure that you can look at like what we did with the convolutional networks to see, hey, we did better than humans. And if somebody thinks of some great way to do that, then that would be awesome because you probably become famous. But at this point, no one's really figured it out. Okay, that is it, and that's like a half hour early, so I don't know if that's good or bad. It feels kind of good, but maybe it's not. Anyways, next week we will do a full week of reinforcement learning. That'll be a whirlwind because there's lots and lots to do on reinforcement learning, and we're only doing it in a week. But maybe that's because this is not something I know very well. I just know the basics of it. So you get the basics of it, and hopefully that'll satiate your curiosity for the time being. And then if you're more curious, we'll go and look into these things. Okay. Have a good evening and have a good weekend. We'll see you next Tuesday. Happy to answer your questions, talk about homework, talk about proposals, anything.
So I have no question. So
Yeah.
what's the story like? Because it's just so is there a reason why this semester